Hey everybody, I'm Archita, a machine learning engineer and community advocate here at Allora Labs. In today's tutorial, I'll be diving into building a custom model or a worker node for Ethereum 12-hour volatility prediction. It's one of the topics in Alora's Forge competition, which you should definitely sign up for. And in today's tutorial, the whole intention is to be able to experiment with a lot of different algorithms so that you can produce better predictions and submit that to the network and essentially earn better rewards. So let's jump right in. Awesome. Before we dive into the code, I wanted to highlight a few prerequisites. The first thing that you would want to do is set up your wallet, and you would do that by installing the Allora CLI tool. This is an important step for you to register and set up your worker node, and the link for this will be given in the description. You could also check out the docs as well. The second thing you would want to do is participate in Allora Forge. Once you set up your wallet, you would provide your wallet address. And in Allora Forge, you would be able to see all the participants submitting their inferences and how their predictions are performing. And that gets pretty interesting. And the final step is to build your custom model and deploy your worker node, which I'll be showing right now. But the first place that you would definitely want to check out is Alora MDK because there are off the shelf models and you can start building on top of those right away and you can submit your worker nodes. I also wanted to provide clarity on the volatility calculation because that's important the way you submit your predictions. So, what you would do is calculate the log of the percentage change in the closing price. And given that it's ETH volatility prediction for the next 12 hours, you would take 720 minutes as the rolling window. So you would be calculating the standard deviation over 720 minutes. So these four files are important for this tutorial. You need to make sure your variables are set correctly in the .env and the config.json file. And then model.py is the meat of this tutorial where the custom model is being built there. And utils.py is the file for having helper functions that I'll be using in model.py. So let's jump right in. For the EMV file, you need to have your token as ETH. I'm taking the last 30 days as my historical data to train my model. And the time frame is 1 minute frequency data. Here, the model I have created is an XGBoost regressor. I've also created a random forest regressor, but this is the model I am choosing to deploy. So I've provided this as the name. And region and data provider, you can choose accordingly. I would suggest to use Tingo as the data provider because that is much more better. And for config.json, you want to make sure you provide your address key name and the seed phrase for your address restore mnemonic, as well as the link for the node RPC. Make sure your topic ID for your worker is set to 28 because that's the topic ID for the ETH 12-hour volatility prediction, as well as the pair as ETH in our case. Now, utils.py is for having helper functions, which is going to be used in model.py. So utils.py is imported in model.py. And I have two functions here. So I want to talk more first about the run model function. So essentially, it is calling the features and target function. So the run model function is taking the data frame, the model that it wants to run, and the list of features and the target variable in string format. So let's look at the get features and target function here. So this is accepting the data frame. This could be train data frame or test data frame or any data frame, in fact. And then you you pass the string of features that you want your model to train on and the target variable. In the feature selection, what it does is it just splits it into all the input data frame by only taking the features columns, and it splits it into Y, which is the target data frame, by only taking the target variable. And that's what we're getting here. And then there's a test split of 80% training data and 20% test data that's happening here. And then the model fits on the training X and Y data. And for the prediction, it does a model.predict on the X test. This is just an extra thing that I'm doing on the backend just to evaluate how well my model is doing. It's a good rule of practice to be able to evaluate how well your model is doing before deploying. You can obviously see how well your model is performing once you deploy without having to do this, but then for you to have conviction about your model and how well it is performing, this is a good practice. And the way you would check that is by printing a few evaluation metrics to see how well your model is faring with the predictions and the actual test data. And some of the evaluation metrics that I'm using is MSE, RMSE, and R square. Then one other thing that I'm also interested about is looking at which features are important for my model. So I'm printing those. And I'm also displaying these MSE, RMSE, and R square as well. And then this function essentially is returning the model object, which can then be used to do a predict on. So coming to model.py, which is the meat of our model, you need to be able to import all the important libraries. Here, since I'm building a random forest regressor and an XGBoost regressor, I'm calling those libraries. And then here you see I am also importing utils and I'm using because I'll be using these two functions. And here I've taken inspiration from the basic coin prediction repository, but then I would highly encourage using Allora MDK because it has a lot of models that you can build on top of. It's already present in that. So here, as you know, it's just getting data from different data providers, Binance, CoinGecko, and all of that. And once it gets downloaded, I wanted to talk more about calculating the features. So here's where I built custom function to do feature engineering. So essentially the data gets downloaded by the data provider. I'm passing it here. And I'm also passing the candle interval, which is the 1 minute frequency data, and the volatility window as 720 minutes, which is 12 hours. And nlags is another parameter that I'm passing to build number of lag variables that I want. So I'm creating lag variables for the log returns and the volume. So that's why I also have this extra parameter. So I am copying the data frame, and if there's any NAs, I'm just like doing forward fill or backfill. Here, there's no NA values in my data set, but that's okay. And now what I'm doing is calculating the log returns. And then here's where I'm calculating the log returns and volume lag features. So I'm providing the range of 1 to 6. So essentially, it's naming the log return t minus 1, t minus 2 until t minus 5. And it is shifting by that number to get the lag. The similar thing is happening for the volume lag features. I'm also calculating two other features, that is simple moving average and exponential moving average of the closing price. So these you can be creative about this and create any features that you think is helpful for the model. So these are some two custom features that I created. I'm also creating another variable, the log returns. I have to calculate the volatility. So I am naming the current volatility. So I am naming the current volatility. I am currently naming the current volatility as the feature, and I am calculating the standard deviation over a rolling 720-minute window. And we also have to define what is our y variable. And this is essentially because you will be predicting the model, the ETH volatility for the next 12 hours. You need to be able to set your target volatility as this. So for the current time, you need to have the target volatility for 12 hours. So this function is returning the data frame and the list of features. Now I'll be using this function in the train model function as well as the get inference function. So here's where I'm reading the training data and I'm loading it. And then here's where I'm calling my calculate volatility features and I'm passing the data frame, giving the candle interval as 1 minute, volatility window 720 minutes. So it returns the data frame and the list of features. And I'm also appending another feature of the closing price. And then here is the list of features, and the target variable is the target volatility feature. Here is where you would add your custom model. So since I'm using a random forest regressor as well as XGBoost regressor, I am instantiating the model objects here. So if you're using any other model, let's say LSTM or ARIMA or any other time series based models, you would add these here. And then from utils.py, if you remember, I am calling the run model function to get the model object. And I'm passing the data frame, the model, which here in our case is XGBoost regressor. We had also defined this in our environment variable. And I'm passing features and target. So now that the model gets trained, it gets stored as a pickle file and it shows the path where it's getting saved. And once that's done, you would want to use this model object to essentially get predictions for your new data. So now you load the model, and once you get the new data, you will then be calling calculate volatility features again on this new data and passing the same variables. It's just that the data frame now changes to X new. And then now you're getting the data frame and the list of features. I'm doing the same thing here as the train. That is printing the close feature and also getting the list of features. And I'm having the target feature as the target volatility. Since I'm doing feature engineering on this new data, um, this is an important step. So now we want to get the features and the target. So I am passing the data frame and the features and the target so that it splits it into X and Y. And then I'm dropping any NA values. And then the loaded model is being called here. And then I'm doing a dot predict so that it predicts the volatility for this X new data frame. So this is the current volatility prediction. And since I want for the latest data point, I am returning this value, which will be printed once I deploy my workload. Awesome. Now that we saw how to build a custom model, let's deploy it. And the way you would do that is by building the Docker container. But before that, just to make sure your environment variable is set properly, you would have to run this command just to make sure all your environment and config variables are set. And then once you do that, you would build a Docker container. So you would give a Docker compose build. And since I've already built it, I'm not running this command. And the next thing I'll do is deploy. And the way I would do that is Docker compose up. So here you saw that these containers created for inference, worker, and updater. And now you'll start to see the logs for these. So essentially now the data is getting downloaded from Binance. And since I already have the data downloaded, there are 0 new files here. And since I've taken the historical data for the last 30 days, there are 63K points. So it's also doing like the model training and the feature engineering in the backend. So it takes a while. So now you see that the data is loaded for the training data from Binance. And then along the way, you should also be seeing any like warnings. You should be able to like resolve those. This isn't a big issue, but then yeah, you should also be able to see any such messages in the logs. And now that we ran XGBoost regressor, you will be able to see some of the print statements that we had given earlier. So you're seeing the MSE is almost zero. It's a very low value. And the RMSE is this value. And then the R square score is 0.55. This is a decent enough model, but then you would also want to make sure you iterate on this and build better models. Some other models that's useful are LSTM or GARCH, which is good for predicting volatility. You would probably want to experiment and also use some ensembling techniques. So after that, some other logs that you see are the input features that we are also submitting. And the Inference is now also submitting the predictions. This is the volatility value that it's predicted for the latest data point. And this is essentially the prediction that's also submitted to the network. Then, to also see if the worker node is correctly deployed, you should also be able to see in the logs. Basically, yeah. So once you see this message as success for this transaction hash, that means that your worker node is successfully deployed and your inference is also submitting the predictions to the network. So this is the end of the tutorial. I hope this was helpful and also helps you build your own custom models and experiment with a lot of different algorithms and features. Do let me know any feedback or comments or any other new topics that you want to see in the future. And thank you so much for tuning in.